Is describing motion, as you can see right there. There are 10 sections in it, and from sections 1.3 to 1.10 we have little experiments and stuff to show you, but for 1.1 and 1.2 we'll just explain it this way. Section 1.1 is the units, and it's basically the MKS system, which is meters, kilograms, and seconds, which all the answers in any physics have to be in. There's also other units like the Newton and Kelvin and amperes, and they're just basically units. Converting units is a simple process. Section 1.2 is the frame of reference, which is that if something is moving, we have to be able to check its position relative to something else. It is just a way to check the position with respect to the surroundings of whatever object is moving. And now, section 1.3 to 1.10, we have little labs and experiments to show you, and so we will.
Can we do that again?
Go. 1.56. Go. 1.18. Go. 1.07. Go. 0.93. The average time is 1.16 seconds. So 2 divided by 1.16. The average velocity equals 1.72 meters per second. Which is how fast the something goes and in what direction it goes. Displacement is part of velocity, and that is the final distance minus the initial distance over the final time minus the initial time. And that is how you find average velocity. And we will do some experiment with Hot Wheels for this section meter in 3.53 seconds. So 1 divided by 3.53 is 0.28 meters per second, which is the average velocity of this car. We can make it look. Do this.
Yeah, no, fast.
You're gonna do this. acceleration, which is either increasing speed or decreasing speed, because there is such a thing as reverse acceleration. And the equation for acceleration is the change in the velocity over the time. And what we will be doing for this section is basically just showing you what acceleration and deceleration are. So there's acceleration as it goes from slow to fast. Yeah. And deceleration is where it goes from fast to slow. That's what deceleration is. And as you turn, you have to slow down for acceleration because you don't want to go crashing into a building like Joe Murray did at one point. And what they want to know is how fast after an acceleration the car or whatever it is will go. And we don't have an experiment for this because we showed you what velocity and acceleration were and what they do in our things for section 1.4 and 1.5. So basically we're just explaining what this is. And to find the final velocity, it equals the initial velocity plus the change in velocity, which goes back with acceleration. And what this will do is just basically another section on velocity and acceleration, which were explained in 1.4 and 1.5. So now we'll go to section 1.7, where we actually have something to show you for. In 1.7, displacement time acceleration. And what we're doing for this one is we're going to launch a Hot Wheel down by this 5-meter track here and see how far it goes in 3 seconds. Because that is basically what the section is about, how far something goes in a given time. Okay, go. Stop. Okay, so the car went 4.5 meters in 3 seconds. And that is basically what they wanted to accomplish in that. And all this chapter, this section has to do with is more formulas for motion. The first one is to find the time. You find the time because it equals the final velocity minus the original velocity over the acceleration. And another one is for displacement, which is the distance equals the original velocity times the time plus 1/2 acceleration times the time squared. Another equation for velocity under acceleration is that the final velocity squared equals the original velocity squared plus 2 times the acceleration times the distance. Over here we have an equation for displacement under constant acceleration, which is the distance equals the original velocity plus the final velocity over 2 times the time. And down here we got all the formulas that we just covered in this section about motion under constant acceleration. We don't have a lab for this section, but we do for sections 1.9 and 1.10, which are acceleration of gravity and is the acceleration of gravity, gravity, the constant, is 9.8 meters per second squared. And what we're doing for this one is we're going to drop two Hot Wheels, which are different masses, from 2 meters to show that they drop at the same time because of the acceleration. Section of the chapter is free fall, and basically what this is, it shows that because of gravity, if you throw something up, it has to come down. So what we're going to do is throw a Hot Wheel from the ground up 2 meters and time how fast it comes down. There we go. And that took 1.28 seconds. Let's do that again. And that took 1.25 seconds. So basically, what that proves is that around 1.26 seconds or so, that's as long as it takes for something to go up 2 meters and back down 2 meters. The whole chapter was the chapter of describing motion, section 1.1 units about the MKS system, chapter 2, or section 2 about the frame of reference, which is where something goes in relative to something else. Section 1.3, speed, which is average speed equals distance over the time. 1.4 velocity. Velocity is the displacement over the time interval. 1.5 acceleration, which is just how if something increases the speed, and the formula for that is velocity over time. 1.6 is just 1.4 and 1.5 together. 1.7 is how far something went in a given time. 1.8 are just more formulas to find motion. In sections 1.9 and 1.10 have to do with gravity and free fall and how fast something will come down, or showing that no matter that things will fall at the same rate from 2 meters high. And from this chapter you have learned basically everything about motion. Joe Marari, John Malinowski, Steve Elmagori, and cameraman Andrew Narrett for Chapter 1.
Chapter 2, Chapter 2 in our physics book is vectors. The first part of Chapter 2 about vectors is about vector quantities. Vector quantities measures the direction and the amount of whatever force is being measured for the vector. Vector quantities are usually measured in an SI unit of force, and they can be displacement, acceleration, mass. It can be several different things for vector quantities. Okay, the next part is vector addition. Vector addition is the addition of two vectors that are either going in the same direction or are in. If they're going in the same direction, you just add the vectors right together to get another force with it'll be in the same direction, but have a larger quantity. Vector addition is also used if two vectors are not in the same direction. They're laid head to tail, and then they're added up with the Pythagorean theorem. R squared equals A squared plus B squared, where R is the resultant. It is the vector going in the direction from the addition of the two original vectors A and B.
And I'm just checking your attitude.
Stop. Okay. An example of vector addition would be if a semi-truck is going west and a car is going north. And when they collide, they'll have a vector, which would be this result. If the car was moving at a certain speed and the semi was moving at a certain speed, this speed would be squared, and this speed would be squared, and that would give you a resultant. You take the square root of the resultant, and that'll give you the resultant vector. And the next section is vector subtraction. Vector subtraction is when two vectors are subtracted from each other, and vector subtraction is one vector is given a negative direction and taken away from the other vector. It would be b minus a equals b plus quantity negative a. And in just a second, Antonio will show you some drawings for that. If the vectors are going in a negative direction, the vector that's smallest is usually given the negative. So when they're added, you'll get a positive answer. And the next section is relative velocity. Relative velocity is using a frame of reference, and the frame of reference could be if there's a boat on a river. The frame of reference could be the boat to the bank, or the boat to the river, or the okay. As I was saying, move on. Relative velocity is if the velocity of the boat relative to the shore. The boat's moving with the river, so the boat by itself is velocity relative to the shore. The river is moving also, so the river has a velocity relative to the shore. And the boat itself is moving against the river also, so it's got a velocity relative to the river. Another example of this would be me and you standing on Earth right now. Relative to the Earth, we're not moving. But relative to the sun, relative to anything else in space, we're moving very fast because the Earth itself is spinning around. And the Earth itself is also moving relative to the sun. The next section is vector addition by components. And vector addition by components means a vector has components, the x and y component, which make up the vector itself. And for vector addition, you can get the resultant components, which are r sub x and r sub y. To do this, you take the components and add them together. The components of the vectors being added. So that would be a sub x, a sub b, a sub c, x sub d, c sub x, and stuff like that. You just keep adding all of them up, all the components, and that'll get you the resultant x. You do the same for y. A sub y, b sub y, c sub y. And when you add those two together, you'll get x, r sub x, and r sub y. And you can find the resultant by doing the square root of r sub x squared, r sub y squared. And just take the square root of that, and that will give you your resultant vector with vector addition by components. And the last section we will talk about is projectile flight. A projectile is an object put into motion that's not rolling across the earth, it's in the air. It usually has an arc, and with this arc there comes an angle at the bottom, which is theta, and that angle can be used to find the time in air, and that formula is T equals 2 velocity initial sine theta over g. G is gravity, which is 9.8 meters per second, that's acceleration of gravity. And you can also find the range of a projectile that's gone through the air. The range is the distance from its initial point to where it lands, and that can be found by the maximum range that it can have can be found by velocity initial squared over gravity, which is again 9.8 meters per second. Okay. And this here is theta, and that's range, as I was just saying. And this arc would be the path of the projectile. And that is chapter 2, vectors. Stop it.
Force and motion. Director, Mark Malinowski. Cameraman, Chris Heiss. Actions, Craig Duchowski. Narrator, Louis Kujawa.
Imagine a ball on a level floor, let alone it stays where it is. If we give it a push, the ball rolls for a while and comes loose. The smoother the ball on the floor, the farther the ball, or in this case car, rolls before stopping. With a perfectly round ball or wheels on a car, and a perfectly smooth and level floor with no air to impede motion, would the ball ever stop? There will never be a perfect ball and a perfect floor, of course, but we can come close. The result is that, as the resistance of motion decreases, the ball does indeed go farther and farther for the same push. We can reasonably conclude that, under ideal conditions, the ball will keep rolling forever. According to Newton's first law of motion, an object at rest will remain at rest, and an object in motion will continue in motion at a constant velocity, constant speed in a straight line, in the absence of any interaction with something else. The reluctance of an object to change its state of rest or uniform motion of property is called inertia. For example, when a car suddenly starts to move, the inertia of the passengers tend to keep them at rest relative to the earth, and so their heads move backward relative to the car. The back of the car also lifts up. When the car suddenly stops, inertia tends to keep them moving forward, and so their heads move forward relative to the car. The car also moves forward. Both effects illustrate the first law of motion. A measure of the inertia of an object at rest is its mass. The more something resists being set in motion, assuming it is able to roll freely, the greater its mass. The object with the greater mass, in this case the white car, has a lower speed, and the object with less mass, the orange car, has a higher speed when being hit with the same force. This is because the more mass something has, the more it is able to resist a change. According to the first law of motion, the velocity of an object, which may be zero, remains constant as long as it does not interact with something else. When the object interacts with something else, its velocity changes. Here you can see that the orange car was moving in a straight line at a constant velocity. When it hit the gigantic tower, it bounced off and changed velocity. A force is any influence that can change the velocity of an object. So therefore, the gigantic tower is a force on the car because it changed the velocity of the object. If no net force acts on it, an object will remain at rest, and an object in motion will remain at motion at a constant velocity. Well, why does the car stop on its own eventually? That's because friction, which is a force that acts on the object, causes it to stop. The second law of motion states the net force acting on an object equals the product of the mass and the acceleration of the object. The direction of the force is the same as that of the acceleration. So when any one of these cars moves in a straight line, its direction of force is the same as the direction it is accelerating. The force with which the earth attracts an object is called its weight. If you weigh 700 newtons, 157 pounds, that means the earth is pulling you down with a force of 700 newtons. Weight, a vector quantity, is different from mass, a scalar quantity, which is a measure of inertia. Weight and mass, however, are closely related. The more something weighs, the more acceleration it has when it's dropped. The mass of an object is a more basic property than its weight, because the pull of gravity on it is not the same everywhere. As you can see, when you put the cars on an incline, gravity has more pull on it because of the car's mass wanting to be attracted to the earth. When a car is laying flat, the car has no real reason to move because gravity is holding it in place. Newton's third law of motion states that when an object exerts a force on another object, the second object exerts on the first force of the same magnitude but in the opposite direction. So therefore, when two cars crash into each other, they exert the same force on each other but in the opposite direction, causing them to change directions.
That has been our presentation.
Yeah, I didn't think that. Can I use
No, it's like
dude, it's
yeah,
it's right there. I can hit Forrest in the head.
Well, if you guys are gonna come tomorrow without any work at all because you don't have a camera, nothing, zero, then you're gonna lose it. Well, then why don't you draw pictures then, if you're gonna give me some excuse that you can't do anything? Because life is too tough for you. Because life is too, what was it? On Tuesday, you sat there and did nothing. On Wednesday, you sat there and did nothing. Today's Thursday, you sit here and do nothing. Tomorrow, you're gonna say, it's not my fault I can't do anything. If you guys are gonna do something back there, ask please. What is this stuff? This stuff right here. Take that out and
Yeah, we should draw more pictures. Here, test flight 8.
The physical quantity called work is a measure of the amount of change in a broad sense to which a force gives rise when it acts upon something. This is a group doing work.
Take them all?
It'll take more time.
What we're gonna do is,
Ah, he almost attacked you with his ball. His ball hit you in the head.
This is another group doing work.
so what we're gonna do is we're gonna measure the
Write down
and we already know what the mass is, it's 100 grams. So, you guys ready? All your stuff looks over. You guys ready?
just about.
Look at them work.
Oh, we worked very hard.
Write something.
Come on, this is a group not doing work.
The sheet anymore.
The word energy is part of everyday life. We say an active person, such as Sal, is energetic. Here's Sal using his energy.
Well, as you can see, the work I did against the wall was done equally and opposite back against me. Let's try again. See, it happens every time, and there's nothing to explain, but that's work. Work both ways.
Are you filming us,
We can see the potential energy of this tennis ball. When fallen from height, we'll just call h, which will stand right here. It will fall faster and faster until it hits the ground. If this wasn't on such a surface where it would bounce, and it could leave an indentation on the ground, we could see the amount of energy used. Here, watch the potential energy as it falls faster and faster to the ground.
I saw that.
Amazing.
Incredible.
Let's see that again.
Slow motion. Oh, we're recording it? Oh, did it? I still think we should have done the summary with everything that happened there. You know? Yeah. Oh my God. I want to see if the rocket came in the front part. Did I ever tell you that Mike James was my favorite student? There's a reason why I didn't.
As you can see, when you saw the one ball up in the air, that was potential energy. Once it hit and it set the other balls in motion, it was using kinetic energy.
Ow.
Here, you want take this, Mike James. Take this.
Ow.
Again. Again.
My teacher's abusive.
Again. Again.
Okay, we're live outside of Mr. Noon's class in second period physics with Chris, Jeff, Matt, and me, Ryan, who's filming so you can't see me. And welcome to the wonderful world of momentum. Here we'll talk about momentum, collisions, other good stuff. That's pretty much it. Let's have some fun. Alright, the chapter we did focuses basically on momentum, which, as you can see, is the equation P equals mv. That stands for momentum equals mass times velocity. Thank you, Jeff. Now I'll talk a little bit more about momentum, and we're going to show it through this next experiment. Well, here we are with Matt and Chris, and we're going to give you an example of that P equals mv equation. Now, Chris has a baseball, and Matt has a tennis ball. Now, a baseball has a greater mass than a tennis ball. So what's going to happen is they're going to both throw the ball against this wall at the same time. Go ahead. Now, what just happened there is that the baseball would have a greater momentum since the velocity was the same and the baseball has the greater mass. Okay, now we have Chris being replaced by Jeff, and this time Jeff and Matt both have tennis balls. So what they're going to do is they're going to throw it at different speeds. Go ahead. And what just happened there is, since both tennis balls have the same mass, but Matt threw one at a greater velocity, Matt's tennis ball has a greater momentum. Now, we're going to show you an example of what we call recoil force. Now, when a baseball hits a bat, and the bat hits the ball, that is an example of recoil force, since it's a force in the opposite direction. Now you have Matt pitching the tennis ball, and you have Chris. Due to a lack of a baseball bat, he's going to be swinging a meter stick. So Matt pitches. Way to go, Barry Bonds. We're going to try that again. What you just saw right there was a perfect example of recoil force. I said, Chris. Here's another example of recoil force. Jeff and Chris's tempers are kind of out of control, so let's see what happens here. That is a great example of recoil force.
Jeff, you all right? Jeff,
Now that we've covered momentum, we're going to be talking about the law of conservation of momentum. Here we have a momentum machine, which we're going to demonstrate that law, which shows that the initial momentum has to equal the final momentum. Now Matt here is going to release the ball. As you see, when it strikes the rest of the balls, one ball goes up, then it goes down, and so on. Now you're probably wondering to yourself, why doesn't this thing go on forever?
And the reason is, although momentum is conserved, kinetic energy is not. Every time a ball strikes another ball, energy is lost to heat, sound, and other stuff. The law of conservation of momentum also applies if, for example, we do two balls. Once again, once the two balls hit the rest, and two balls go up on the other side. Let's try it with three. I don't know about you guys, but I think that's pretty amazing. Now let's say one ball on each side. Yeah, it's 4 balls on each side.
What's going on here, guys?
Here's our special guest,
Stop,
Sal Gaffney.
How you doing, man?
Sal, we're gonna have to ask you to leave. I'm sorry.
All right, I'm leaving.
Bye. Sal's a good guy. Now we're gonna do one on each side. Wow, that was let's try that again, huh? Yeah, that's the stuff. Law of conservation of momentum applies to pretty much everything. Now let's try 2 on each side, by suggestion of Chris Burdick. Wow, unbelievable. And that is the law of conservation of momentum. Now we're going to talk about collisions. As we read in our chapter, there are 3 types of collisions: elastic, inelastic, and completely inelastic. Right here we're going to show you an example of elastic. It's one where none of the kinetic energy is lost in the collision. Now as you see, we have one car standing still, and Matt's going to roll the other car down the track. Let's see what happens. All right, let's try that one more time. All right, what happened there, or what was supposed to happen there, was when the 2 cars collided, the white car had the same momentum as the other one did when it hit it. And that's the bell signaling the end of second period. We're going to try it one more time. And that is an elastic collision. Here's an example of inelastic collision. Now the 2 cars both went at each other with momentum, and when they collided, only some of the kinetic energy was lost. And there's an inelastic collision. Here's an example of thrust. No, not that kind of thrust, the other kind of thrust. Thrust with, like, let's say, a rocket. Now, when a rocket's on a launching pad, the total momentum is 0. When it's fired, the exhaust gases push up on the launching pad, as Jeff will demonstrate. Contrary to rumor, rockets do not operate by launching against the launch pads. That's not how they get up into space. And they operate best in outer space where there's no atmosphere to slow down their motion. Thank you, Jeff. All right, let's go over a review of all the important things we've gone through in this chapter. Linear momentum of an object is the product of its mass times its velocity.
Well, then, come on.
It's referred to simply as momentum.
Right over here, just like I said. No one's
The
here.
conservation of momentum states that although the kinetic energy of an object may change, the total momentum will not. The thrust of a rocket is not determined by gases pushing up against the launching pad when its initial velocity is reached. The elastic collisions conserve kinetic energy. Inelastic conserve some kinetic energy, and completely inelastic do not conserve any kinetic energy at all. That's
momentum.
Ladies and gentlemen, this is the wonderful world of momentum. It's a wonderful thing.
Rather than a horizontal circle. The object's total energy remains constant, and all of it is kinetic energy at the bottom of the circle. At the top of the circle, however, the total energy is divided between the kinetic energy and the maximum potential energy relative to the bottom. So the object's speed is least there, at the bottom. The motion is circular, but not uniform. The object goes faster as it goes downward and slower as it goes upward. Now, the big effect here is centripetal force. Eric's hand is the centripetal force.
The center force.
The center force. The centripetal force is the force perpendicular to the velocity of an object moving along the curved path. In this case, the string and the ball, forming the curved path. The centripetal force is directed toward the center of the curvature of the path, that being Eric's hand.
All right, I'm going. Yeah, that was a great loop. Now we got Pat.
Now, let's take for instance that this was an actual plane with a pilot. The upward force on the pilot exerted by the airplane's seat equals the force needed to support the pilot's weight, plus the centripetal force needed for a pilot to move in a circular path. Now the downward force on the seat exerted by the pilot equals the pilot's weight plus the reaction force to the centripetal force.
All right, now here we're going to be getting on the expressway on an in-ramp, and like right here, for instance, centripetal force is going to be acting with us, and my velocity is going to be working against us. You see how the road is banked a little bit on an angle? That's keeping my car from flying off into the ditch. Now I'll show you a little bit more when we get up to the ramp. See, the friction of my tires and the weight of my car keep me on the pavement, and centripetal force also helps me keep me on the pavement. What tries to get me off the road is my velocity going straight. Now when I hit this on-ramp, centripetal force, my weight, and the friction on my tires is going to be helping me to stay on the ramp. You won't be able to see it too much right here, but the road is angled up, and that helps to keep me here too. And speed, like if I increase the speed, it'll try to get me out more into the ditch. Now this is an example of centripetal force. It's trying to push me that way. Now I'll show you a little something where the centripetal force is less than my velocity. Don't try this at home, kids. Now it's getting pretty tight. I don't know if you guys heard that, but yeah, it was kind of squeaking right there. And that was where my velocity was higher than the centripetal force. And it was trying to push me out and away. The centripetal force keeps keep me in, friction on my tires, and the weight was keeping me. All right, now I'm gonna try to pull off something where the centripetal force isn't enough to keep me on the pavement, but see right there, centripetal force was less than what my velocity was. It was greater. And that's what kept me sliding. All right, now I'm going to demonstrate gravity, and I am going to jump off my garage. Okay, I'll see. I think I broke my leg on that. Yeah, well, that's gravity.
Oops.
Yeah.
Miscalculation. I recorded this. Why am I just wasting my time? God, that's beautiful. You just messed everything up, Joel.
It's like 10 minutes and I'm actually pushing.
Oh, I was going the wrong way.
Alright, just go.
What was that?
You know,
Start doing something.
we're gonna,
Go.
who's gonna see
Start
this?
doing. It's been like 5 minutes. Start doing
Oh, okay, what we're gonna do is, we're trying to figure out the force constant. See, what we're gonna do is we're gonna measure the oscillations, the number of oscillations, and the period. And we already know what the mass is, it's 100 grams. So,
You guys ready? All your stuff was
God, I have to do everything in the screw. Like this, Joe.
No? Tell me when you're ready, because you gotta get started.
hold on.
That's not how you do it, Joe.
Press stop.
Mark, you might want to stop the video camera for this.
Just a little bit.
Are you guys ready? I'm asking you.
Mark, you might want to stop the video camera for this.
Press the red button.
Oh, and here comes Mark Stevenson. Hello, Mark. How was your day?
That's good. Oh, so yeah, we're trying to continue the process. So right now we're just trying to find out the period of basically of this mass. So what we're doing right now is, I know there's a zoom button.
Making the object's velocity.
How are we gonna put this on?
John, have you guys taped anything yet?
No, we're getting it all together.
All right.
Press stop.
Don't worry about it.
He just showed up.
You want me to explain it while you explain it?
Come on, Mark. Help us out here.
Yeah, we're
Joe does not know what he's doing.
Oops. Background. Reading from the book.
You know, push it.
Yeah, I thought that one had him hooked on it.
Alright.
Press stop. Okay, just leave it.
You guys can come over here.
Okay, yeah, we got it. So basically what we're gonna do is just, we're gonna count the number of times oscillations this mass goes from here to here, and then we'll record the time. Ready? Count it. Go. That was the test run.
My toilet, let's do it.
Let's go. Ready?
Wait.
Not so hard.
Not so hard. Go.
Things don't stay on there, right? We'll get ready.
Don't pull us down. Ready? Go. 1, 2, 3, 4, 5, 8, 9, 10. Okay. 10 seconds, 10 oscillations, it was 6 seconds, so basically it was 3 seconds for one
oscillation.
Yeah.
What a dumb.
Yeah, so we've put that in our
Equation.
and we solved for the force constant. And we know the mass is 100 grams, so if you just set that up in your equation, which is, once again, T equals 2 pi times square root mass over K. And then all you gotta do is rearrange that equation, you can figure out the force constant.
What's the answer?
The answer is K.
K equals what?
Newton over meters. And we're done.